So, welcome to my presentation. Today I will talk about asynchronous computations in JavaScript. So, the question that we need to ask ourselves first is, when does this matter? Or in other words, how can I make my browser sweat? When you're writing your day-to-day applications in JavaScript, when you're writing some form, you probably don't run into any computational issues. The code is probably running fine enough. There's probably not that much happening actually to make the browser sweat. But there are some applications when stuff might actually matter. For example, you can have 3D animations. So you can have a 3D animation, some textures, some bump maps, whatever. Let me make it a bit brighter. Okay. So that's not sweating the browser well enough. So let's add some lights. Okay, we have some lights. Still 60 frames per second. That's not enough. Let's make the lights crazy a bit. Still about 60 frames per second. What does this mean? That means that the browser is not doing more than 60 frames per second. Why? Because this projector and this screen that I'm running right now, it's running at 60 Hertz refresh rate. So there's no point in the browser actually rendering this stuff any faster. So what else can we add to make it a little bit slower? Well, everybody loves particles, right? So let's add some particles. Right now you can see that there are particles added to the animation, but it's still clocking at about 60 frames per second. So what does that mean? That means that even this kind of animation is not that hard for this computer to actually render. But it's close enough, trust me. If we let it run for a bit longer, if those particles are actually, the number of particles increases as this animation goes. If we got to this maximum 10,000 layers of particles, we would actually see some slowdown. But we don't have that much time, sadly. So what else does make browsers sweat? Well, pure computations. Python doesn't do computations very well, and JavaScript also, interpreted language, it doesn't do computations that well. If you were interested in mathematics, you probably recognize this pattern that is displayed right now. This is the Mandelbrot set fractal. Fractals are a fascinating piece of mathematics. It's a set described by an equation on complex numbers. The cool thing about it is that they are actually infinite in their detail. So as you can see right now, the browser is computing this fractal thing on the fly, and it's zooming in on the detail. And as you can see, the resolution of the fractal is infinitely detailed. We can zoom in, and there's still new details rendered. I encourage you to look this stuff up if you haven't seen it yet. And you can see that this fractal is being rendered at quite low frame rate. 2 frames per second, that's not very fast. Why? Because this fractal calculation is actually quite troublesome for the CPU. It requires lots of operations. How does the fractal calculation look like? Well, imagine that we have the screen that is of particular resolution, and we need to, for each pixel of the screen, we need to run some code. Basically, look at this line. This is the important line. For each row in the output picture, we need to execute some code that will run for each column in that row, and will execute the function getFractalValue. The important thing is that we are running for each row and then for each column. And later on, when I will be showing you how to make this a little bit better, you will need to remember this. The other important thing is that the fractals, they are very stateless. So to calculate a particular pixel in the fractal, you only need to give it the coordinates. So I'm starting here with the rows and columns in the picture. So that's from, let's say, 0 to 1024. And then I'm transforming them I'm transforming them to the coordinates in the fractal space. So this is to some, the fractal is actually between some numbers. It's like -2 to 1 on the scale. So this is basically mapping it to this scale. So the important thing is that to calculate a particular point in the fractal, you just need the coordinates and that's it. So what does that mean? It means that the fractals are something that this is an actual mathematical term. The fractals are embarrassingly parallel, so they are very easy to calculate because you can calculate actually each pixel in separation because there's no common state that you need to keep. Each pixel can be calculated in total separation. So they are pretty good for like spreading between multiple cores and so on and so on. So now the calculations in JavaScript. As we all know by now, probably, JavaScript is single-threaded. What does that mean? It means that there's a single event loop, and let's say that a user clicks on our page. What happens? User clicks on a page, and there's a handler attached to this click event. So user clicks, then the browser starts handling this click. While handling this click, let's say that the user clicks again. What happens? Well, the second handler won't execute straight away. It will need to wait. The handler will be added to the event queue and will be scheduled for later. So first we need to finish handling the first click, then the browser will probably repaint, and only then it can handle the second click. That's basically it. We have a queue, and nothing can happen at the same time in JavaScript. So how do we make animations in JavaScript? Well, it's not a new API because it's been there for some time, but it's called request animation frame. It's quite simple to use. Basically, you are calling this function with a callback. You are saying, before you do the next repaint, please execute the function that I'm giving you. So in this particular example, I'm giving it an update function. This update function basically updates the scene. So if I have a 3D animation, I will move the particles or do whatever else I need to do. And then I will schedule the next run of this function. So I schedule this callback, and this callback schedules itself to be executed before the next repaint. So how does this look in the JavaScript engine? First, we execute the update function. Then at the end, the function schedules itself. Then the browser can repaint. And then the browser knows that there's a scheduled callback that it needs to do before the next repaint. So it executes that callback. Then the callback schedules itself again. The browser can repaint. And this process continues, and that's how we get an animation. Depending on how long does the update function take, we'll get a different frame rate. The browser knows that it shouldn't do more than 60 frames per second because it doesn't make sense. So the maximum is set. But if I would make the update function take really long, then it won't finish before the next repaint was supposed to happen, and then the frame rate will drop. So instead of getting 60 frames per second, I would get, for example, 30 frames per second. So let's do something cool. We saw that we can have animations. We can also have fractals. So what if we would have them at the same time? Wouldn't that be cool? So let's try doing that in a synchronous way. So you remember when I showed you that calculating the fractals is basically for each row you need to execute some function. And this is like a wrapper around that. So this is basically, let's say that this is an implementation of Python's range function. So you get the range end. So for example, you give her 10, and for integers between 0 and 10, so 0, 1, 2, 3, up to 9, you'll execute this callback that is called here iteration callback. And then at the end of the function, when everything finishes, I will execute end callback to notify that all my calculations are finished. So this is totally synchronous. All the calculations need to happen within this function, and only then we can say that stuff is finished. So using this approach, I will calculate the fractals, and I will include them in my fancy animation. So I have my lights, I have my particles. You can see that after a while they are running at 60 frames per second. And now, boom, I'm adding the fractals. Oh, this is no good. What kind of frame rate is that? That is not animation at all. Why? Because the fractals, they take too long to calculate. They can take more than 1 second to calculate. So basically, what happens is that the animation is being starved. It doesn't execute often enough. So this is what happens. We start the update, so we update the 3D particles in the screen, for example. Then synchronously we are calculating the fractal. Then we are coming back to 3D and we are drawing the fractal that we just calculated. Then we schedule the next animation frame, and only then the browser can repaint. But actually, the browser wanted to repaint here when we were doing the fractal, when we were in the middle of the fractal. Well, we didn't give it a chance because something else was happening already. The fractal was being calculated, so it didn't get a chance to repaint. That's why the frame rate drops. And then the story repeats itself again. We are doing the 3D, then the fractal, and the browser didn't get a chance to repaint on time. Okay, so we know that synchronous approach is not good enough. So how about we do some asynchronous approach? So how do we do the fractals asynchronously? Well, let's say that in the update function, we will first update our 3D particles and other stuff. Asynchronously, we will ask for the fractal to be calculated. And if the fractal is calculated, then we will just save it to a variable. And in this function, update scene, if at this particular run of the update function, the fractal data is available, then we draw it, we clean the data, and we request the next fractal frame to be calculated. So basically, the fractals and the 3D models are decoupled. So the animation goes on as it was, doesn't wait for the fractals, and the fractals are happening on its own. So basically, there are like 2 animations running concurrently, the main 3D animation and the fractals, and they're running separately at different frame rates, of course. And this way, we shouldn't get such a bad result as before. So how would we implement the batched fractals? So we want to calculate the fractals asynchronously. So we don't want the whole thing to be calculated in one go. We want to do it in batches. So we would like, for example, to calculate not all the lines. So if the picture has 512 lines, to be rendered, we don't want to calculate all of them at once. Let's say we want to do 5 of them at once. So we'll do about 102 batches of calculation, for example. So this is a function similar to the one that I was showing you previously, the synchronous iteration. It's basically gets the same parameters, so the end of the range. So this is, for example, the number 5012, the iteration callback, and what should be executed at the end. What happens, we first determine to which index do we go in this particular batch, and then we are executing the iteration callback as many times as the batch size would want us to do. So, for example, if we want to do 5 lines at a time, we'll execute this particular callback 5 times. Then we just need to check if we reached the end, or we didn't reach the end and we still have some stuff to do. If we reach the end, then it's time to execute the following callback, so to notify that the calculations are finished. If we didn't finish, then we need to schedule another run of this function, just with starting from the index where we left off. So we schedule that the work should resume where we left it off, and then we call set timeout to schedule the next callback. This is pretty straightforward. You've probably seen this approach in some JavaScript code already. So let's see how this performs. So we have our fancy animation. Let me increase the brightness a bit. We have our particles. We are running 60 frames per second, and then we want to do the asynchronous thing. So you can see that the frame rate dropped and that the animation is, well, it's better. I mean, you can see that this is an animation, stuff moves, but it's not very fluid. It doesn't run that smoothly. The rate of the main animation is it's different at different times. Let's say 30 frames per second, while the fractals are under 1 frame per second. So you can see that they are really running at different speeds. You can see that the animation is sometimes slowing down and sometimes running a bit faster. This is because there are two phases of the fractal calculation. First, we are actually calculating the values, and then there's another phase where I'm calculating the coloring to make it in those nice shades of different colors. And that coloring is actually faster than calculating the fractal. So when the animation is a bit faster, that's the stage where it's calculating the hues to display, which don't take that much time up. So that was not great. What happened? Our 3D animation was executing, so we updated our 3D models. Then we scheduled the fractal calculation to execute with a set timeout, and we requested the next animation frame. Then the browser had the chance to repaint, and then we started executing the first batch of the fractal calculation. After that was done, we scheduled the next batch to be executed with set timeout. Meantime, the browser figured out that we need to repaint the screen soon, so let's execute the update function. It executed that. It scheduled itself again, managed to do a repaint, then another fractal batch, and so on and so on. At some point, the fractal was ready. And then in the 3D update, we took the fractal and we drew it. Then we scheduled the next fractal frame to be executed. We scheduled the next 3D update to execute, and the browser managed to repaint. So that was not so bad, and you can see that the animation was kind of working, but it was not working very fast. Why? Probably because this fractal batch was executing for too long. If it would be really small, then we probably wouldn't see it. We wouldn't see that it's affecting the main animation, but it was probably too long. How can we know how long should we actually spend calculating this stuff? Well, that's the thing, we cannot know. If we take the batch to be too small, then our calculations are split into too many batches, and they will be just slow, because there's a timeout between the finishing of previous batch and starting the next one. So it's even if the 3D wouldn't start straight away, between batches there would still be some padding. There would be still some time where the browser would be idle. So if we have the batch too small, then we are losing time because our fractal is not calculating as fast as it could. But if it's too big, then the calculations take too long and the 3D update doesn't happen on time, and we get this jagged animation, which doesn't look good. So it's very hard in this approach to set the right size of the batch to match all the possible scenarios. Because on my computer it might work like this, but on your computer maybe you have a better graphics card or a better processor and it will work better, so you would actually want the batch to be longer. So how can we solve this? Well, there's a new API. The API has a very fancy name. It's Cooperative Scheduling of Background Tasks, and it's a pretty cool API. It's a bit work similar to requesting animation frame, a little bit similar to set timeout. There's a new function on the window object called request idle callback, and to this function, when you are calling it, you are saying, browser, if you have some free time, please execute this callback, which contains calculations that are not mission critical, that are not, they can be done in the background when you have some free time. So only when you have free time, please execute this callback. So this is very similar to set timeout a little bit, but the difference is that the callback will get a deadline object. This deadline object has special functionality that we don't get in set timeout. The browser, when it gives us the opportunity to execute those calculations, it also gives us a time frame. Browser knows that it needs to do the next repaint in, for example, 50 milliseconds. So it knows that it can only give us 40 milliseconds now. And we can learn that we have those 40 milliseconds because we can check on the deadline how much time do we have remaining. So our calculations should only happen if we still have some time remaining. Only then we can do them. And we are doing them for as long as the deadline did not exceed. So we are doing those calculations as long as we have time. When we don't have time, we stop the calculations. If we still have more work to do, we will say that next time you get a chance, please execute some more calculations. But we are doing this stuff only while we still have time. So this is pretty neat. The other thing here, did timeout. This flag can be passed to our function. This deadline flag, this did timeout flag, it has a special meaning. When we are scheduling the callback, we can also say that please execute this when you have free time, but no later than a specific timeout. So we can say that we want this to execute when you have free time, but no later than in 5 seconds. And if by any chance we didn't get a chance to execute it before 5 seconds, then this callback will be executed forcibly, and this flag, the timeout, will be set to true. So then we know that we are like forced to do those calculations. Okay, so let's see how this would look like if we were to implement the function of iterating over a range of numbers. It's very simple, very similar to the one I showed you before with set timeout. Basically, we are iterating as long as the time still remains, as we still have some time by the browser left to do, and that we don't exceed our range. So we are executing this stuff. And then we do the same. We determine if we stopped the loop because we finished all our work that we are supposed to do, or we ran out of time. So in this approach, we can execute the batch can be as long as the browser allows us to be. So if the browser gives us 40 seconds, we can spend all those 40 seconds doing our calculations, which is pretty cool. So let's see how this looks like if we do the animation, brightness, okay. Okay, so we have our particles, 60 frames per second, and now I'm asking for the fractal to be calculated. And you can see that the frame rate is pretty good, the animation is not that bad. This is pretty cool already. This is an acceptable result already. And you should notice that those calculations are done on the main browser thread and they are not slowing down the animation. So this is a pretty cool new API that gives quite good results, I must say. Let's see what happens. We execute our 3D update, so we are updating our 3D objects. We are requesting this idle callback, so we are saying, if you have some time, please calculate my fractals. We are scheduling the next frame of the animation. The browser can repaint. Then the browser can start the idle callback. And within this idle callback, we are checking, do we still have time? Yes, so we calculate. Do we still have time? Yes, so we still calculate. Then we are checking time. Do we still have time? No, we don't have time, any more time. Okay, then do it. We'll continue later. Then the browser can do another 3D frame. It can schedule another 3D frame. It can repaint, and then the browser will resume with the second batch of the fractal calculations. We'll check time. Then we'll figure out the fractal is ready. We'll pass it to the browser. So this is pretty neat. This works pretty neat. We can do the animations pretty smooth on the main thread, which is pretty cool. The only problem is that it's not supported across all the browsers. It's a pretty new API, and as you can see, it's supported on Firefox, Chrome, Opera, and on Android, but it's not supported in any of the Microsoft browsers, which shame for them. There are polyfills for this which are using set timeout. So you can get similar API, but in IE the polyfill won't work as well because it doesn't know how much time do we have. It just, I was looking at the polyfill and it just assumes that we have 50 milliseconds. So that's how it works. So how can we improve upon that? Well, there's one more thing. There's web workers, which you probably know. In JavaScript now you can have stuff, calculations that are executing off the main thread. And this stuff that is executing off the main thread is called web workers. How do we do them? Well, web workers need a separate JavaScript file. Here I call it worker.js. This is the client, so this is the main web page code. So we create a new worker, giving it the name of the JavaScript file, and then we communicate with post message. So we can send some message with some parameters to the worker, and the worker sends us the message event to notify us that it did some work and here's the result. And at the end of our journey, we can also terminate the worker forcibly if we choose to do so. How does the code for the worker itself look like? Well, it's not very different. The worker is listening for the message event, so it waits for the main page to let it know that something needs to happen. Then it needs to calculate some data, and then it communicates back to the main thread with post message. So the API is very, very simple, and the web worker is executed off the main thread. So let's see how this performs with Bright. So we have our particles, 60 frames per second, and then I'm asking for the fractal calculations to happen. So you can see that the animation is rather smooth, but you can also notice that it's like jagging from time to time. Like it's doing fine, but then freezing for half a second and then continuing on. Why is this happening? That's because the data that I need to pass back between the worker and the main thread is quite large. I'm sending those big images of the fractal, which is basically a large bitmap uncompressed. So in this particular example, this is 1.6 megabytes of data to be sent with each frame. So if we want to encode it in a traditional way as an array and send it back, then this serialization and deserialization, it takes a while. That's why you see these hiccups in the animation. But there's, of course, a cure for that. We can use something called transferables. When the worker is sending stuff back, and it uses one of the typed arrays, so a low-level array of elements that are all of uniform type, we can send to the worker, from the worker, not the array itself, but the underlying buffer, which is even a lower level structure that contains basically the data from here. And to post message, we can pass a second argument, which is a list of transferable objects. And this object, so the buffer from this array that we created here, will be passed on to the main thread, but passed on like completely. Like the data, the ownership of the data passes from the worker to the main thread. That means that if I put here something that would try to print me what is in my array, it would turn out that my array is empty because the data vanished. It was actually taken from that thread and given to the main thread, and the data, the ownership changed, and this array, it lost the data because it was taken away from it. That's why it's so fast, because you don't need to serialize this stuff and deserialize it on the other part. You basically transfer memory from one thread to another on a lower level. And thanks to that, our animation now should work without such hiccups. So we have the particles, 60 frames per second. And now we are calculating the fractals of the main thread, and you can see that the animation is pretty smooth. It's not clocking at 60 frames per second. No, I will get back to this, but basically it's smooth. It doesn't have any visible hiccups, and it looks pretty nice. This is the best we can do at this moment to have the calculations done of the main thread. And the animation is executing the main thread. The calculations are of main thread. 2 cores on the computer are used, and it looks not that bad. So now, how does it work actually? Well, we are updating our 3D scene. We are sending post message to the worker, please calculate me the fractal. The worker gets this message. We schedule the next animation frame. We repaint in the browser. Meantime, the worker can calculate the fractal totally synchronously. At the same time, the browser can do many cycles of update and repaint, so the animation is kept nice and smooth. When the worker is done, it sends post message. The main thread gets it, stores the fractal data. Next update it gets, it will draw the data and ask for the next fractal to be calculated. So this is pretty cool. The main animation is not interrupted by anything. So you saw that the animation is no longer running at 60 frames per second, and you might be thinking, this worker is not that great because it actually slows down the animation that we saw. Well, it's not exactly true. The problem that we are no longer having 60 frames per second, but more like 50 frames per second, is just because we are using the textures. This animation that I will show you now, this uses pre-computed fractal data that I computed earlier, and it's basically just fetched over the network and displayed. So there are no calculations done, just fetch over the network and displayed. And you can see that just this displaying and uploading the new texture to the WebGL context, that itself is taking some frames from the animation. So it's not entirely fault of the web worker or communication. It's just because the replacing the texture every so often is actually a bit painful to the browser. It gets even worse at times when it needs to do some garbage collection. What I haven't mentioned, apart from those web workers that I described right now, you can also have shared workers. Those are workers that can be shared between few instances of your page running. So you can have one thread across, for example, 3 tabs in your browser. There's also a thing called service workers, but they're a totally different thing. They're also workers, but they're more on the HTTP protocol level. Thank you for your attention. Do you have any questions?
Hi, my name is Oscar.
Hey.
And I would like to ask you a question. How the data on the low level were passed? Was it passed without a copy at all? Or was it a pointer? Or any other solution? Because as far as I remember, you mentioned just low level.
Yes. So the buffers that were passed, they are low-level structures which describe the data in a very general way. The buffer it just has the pointer to the data and it knows the length of the data, but it doesn't know, for example, the type. And well, you are asking how is this passed? I would say this is kind of a browser implementation detail. I would say it cannot be passed just by pointer because the browser has the main thread in one process and the workers in another process. So it's probably not just straight pointer passing because those two exist in 2 different processes or in different threads. So I'm not sure it can be simple pointer passing. I would rather say that it's probably some memory sharing thing. But this is more of a browser implementation detail.
I understand. Okay, thank you.
Hi. So in general, if you spawn the worker, does it actually spawn the new process in the operating system, or it is just a separate thread? How is it implemented?
Once again, this is a browser implementation detail. When I was looking at the task manager, actually I cannot. I don't know how to answer this question. It's probably a separate thread.
All right.
actually.
Is there any possibility to run the workers in the like old-fashioned way, like spawn a few threads and do not explicitly signal from the main thread to the worker thread?
Once again,
Without this explicit signaling from the worker thread to the main thread, I mean, from the worker to your main page, is it possible to just do some calculations and wait until the thread is done, or like they join?
I mean, you can do those calculations, but you need to use the result somehow. The worker, thread, it doesn't have access to the page. It doesn't have access to DOM, for example. So it cannot, for example, render the result in a div or something like that. You need to pass it back to the main worker. The context that the worker is running in, it doesn't get the real window object there. So you don't have access to the document, you don't have access to many of the APIs. For example, the workers, they don't get access to this request idle callback thing because the workers, they don't have time limit. So this thing doesn't make sense for them. They just run.
So is it possible to wait until the worker is done? I'm done with something in the main thread, but I need some data from the worker. So may I wait for the worker? Or I just
no. You need to use the post message. You don't have any other mechanism of querying if the state of the worker.
So I need to explicitly say that I'm done with the work.
Yeah. The worker is not like spawned and then executes some stuff. No, it's waiting for messages. When you spawn the worker, it's there and it's staying there. If you don't terminate it, it will stay there until the page is closed.
Perfect. Thanks.
It just it stays in the memory.
Sure. That's it. Thanks.
We'll thank Tomek if there are no many questions. So thank you very much for your great presentation.